In this module, we'll tackle a core question. How do large organizations decide which identities and systems to trust? PKI architecture is the framework that makes that decision enforceable. You'll see how roots, intermediates, and policies come together to create a resilient enterprise-wide trust model. Designing PKI means turning abstract security policies into rules that machines can actually enforce. The most useful way to think about it is as an operational trust model built on 4 pillars. Authentication answers, "Who are you?" and is enforced with certificates that bind identities to keys. Confidentiality asks, "Who can read this?" and relies on encrypting data with keys issued under those identities. Integrity is, "Has anything changed?" and uses signatures and hashes to detect tampering. Non-repudiation asks, "Can you later deny doing this?" and depends on strong key protection and auditable issuance. As we go through the course, every PKI design choice will connect back to one or more of these pillars. In PKI, trust depends as much on clearly defined roles as it does on cryptography. The registration authority handles identity proofing. Its job is to confirm, yes, this entity is who they claim to be. The certificate authority relies on that decision. It issues certificates based on the RA's assurance and is accountable for following strict issuance rules. The subscriber is the key owner. They must safeguard their private key and request revocation if it's ever compromised. Finally, the relying party validates certificates and decides whether to trust them in a given transaction. Separating these responsibilities creates audit trails, limits abuse, and makes failures easier to detect, investigate, and contain. For PKI to be useful, other systems must be able to find certificates and check whether they're still valid. Discovery is enabled through structured publication. Certificates, and often CRLs, are pushed into predictable directory locations, like Active Directory or LDAP. That lets applications automatically look up the right certificate for a user, server, or device, instead of hard-coding keys or copying files around. Invalidation is managed through revocation services. You can think of each TLS or smart card check as passing through a turnstile. A valid, non-revoked certificate is waved through, a revoked one is blocked on the spot. Publication and revocation together keep trust both scalable and reversible. Revocation operates in 2 main modes, batch and real-time. With CRLs, a CA periodically publishes a signed list of revoked certificate serial numbers. Clients download that list on a schedule, then make local decisions. It's simple and scales well, but revocation status can be stale until the next update. OCSP inverts this approach. The client asks an OCSP responder whether a specific certificate is good, revoked, or unknown. That delivers near real-time answers, but it introduces online dependencies, latency, and privacy considerations. Most enterprises blend both methods, choosing the mix based on risk, scale, and performance needs. Within a PKI, the root CA is the ultimate trust anchor. It's a self-signed certificate, and every other certificate in the hierarchy eventually chains back to it. Operating systems and browsers decide what to trust based on their root stores. If your root is trusted, everything it properly issues can be trusted as well. That's why the root must be offline or extremely locked down. If it's ever compromised, your entire PKI is effectively dead. A PKI hierarchy is fundamentally about delegating trust so you can contain risks. The root CA remains your ultimate anchor, but you want to interact with it as little as possible. Instead, you introduce intermediate CAs that each represent a specific policy. For example, one for internal use and another for anything exposed externally. Beneath those, issuing CAs handle concrete use cases such as user identities, devices, web servers, or partners. If an issuing CA is compromised, you revoke only that branch, not the entire PKI. This layered structure provides policy separation, operational scale, and strong control over the blast radius of any failure. Choosing a tiering model is one of the most important PKI security decisions you'll make. A single-tier CA is operationally simple, but every function and key sits in one place. If that CA is compromised, your entire trust fabric collapses. A 2-tier model moves the root offline and delegates issuance to an online subordinate. That's the practical baseline for most enterprises. Multi-tier hierarchies add additional intermediates to support separation of duties, environments, or use cases. Security and isolation improve, but so do complexity, latency, and operational overhead. The offline root paradigm treats your root CA like a crown jewel that almost never leaves the vault. It has no network connection at all, so remote attackers simply can't reach it. When you do use it, you follow strict scripted key ceremonies with at least 2 people present and full audit logging. The root keys themselves stay inside an HSM, providing strong physical and logical protection against theft or misuse. Before you design PKI, you decide which world you're operating in. Enterprise PKI focuses on private, internal trust. You control the root, the policies, and who receives certificates. Governance follows your own risk tolerance and business rules, so you can optimize for scenarios like device identity, YFF, VPN, and internal TLS. Public web PKI is a different universe. Trust is global and shared by browsers and operating systems. Governance is enforced through external audits and CA browser forum rules. The emphasis is on internet-facing sites and public APIs, where a single mistake can affect the entire ecosystem. Now let's connect the pieces into an enterprise trust architecture. At the top is the offline root, defining ultimate trust but rarely used. It delegates everyday operations to online issuing CAs, which enforce policy and sign certificates. Directory services support registration, publication, and discovery of those certificates. Subscribers, your servers, devices, and users present certificates for authentication and encryption. Relying parties, such as browsers or applications, validate those certificates and check revocation status, often through OCSP. As a PKI engineer, your role is to align this entire chain, hierarchy, supporting services, and policies with your organization's risk profile and operational realities.